Hello, welcome to College Algebra, section 5.2. My name is Rob Reynolds. Today we're going to be looking at some properties of rational functions. We're going to be looking at vertical asymptotes, horizontal asymptotes, x-intercepts and y-intercepts, and trying to graph rational functions without even using a calculator. So rational functions is, remember, first 5 letters of a rational is a ratio, so it's anything that's in fractional form. Basically, you need to have an x in the denominator. So anytime you have an x in the denominator, it's a rational function. So you could have 3x divided by 4x. That would reduce pretty nicely. So, but this one would not reduce. You cannot cancel part of the sum. So this would be a nice rational function. Or any kind of degree. You might have a squared up top or a cubic down bottom. All of those are rational functions. So our first rational function is just the basic y equals x. You're going to find out that we have this horizontal asymptote because the degree of the numerator is less than the degree of the denominator. The degree of the numerator is a 0, the degree of the denominator is a 1, and anytime that the numerator is less than the denominator, we're going to explore today that we're going to have a horizontal asymptote at y equals 0. To find the vertical asymptote, all we do is set the denominator equal to 0, and when we do that, we get a vertical asymptote of x equals 0. So this is kind of interesting. We got a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. So, and we don't have really any x or y intercepts because if I try to find an x-intercept, I'm not going to have any, because to find x-intercepts, we set the numerator equal to 0, and 1 never equals 0, so there's no x-intercepts. And to find a y-intercept, I let x be 0, and if I let x be 0, I'm dividing by, so there's no x-intercepts, no y-intercepts. Kind of makes sense, because I have asymptotes there. So what I would do is I'd do a quick let statement. If you let x equal 1, then y will also equal 1. So just kind of a quick t-chart. Let x be 1, y be 1. So there's a point. I'm going to swoop towards my asymptote, and there's your first look. Oh, by the way, if this goes to positive infinity on the right side of this yellow line, it's a single asymptote because it's x to the first, then it's going to pick up from negative infinity. It should always alternate from positive to negative. So I'm going to start calling this vertical asymptote dad, because if you were with me in earlier lessons, Mr. X has 2 legs, he stands up, where Mrs. Y, she's the horizontal line, and she's only got 1 leg, so she's the horizontally going as like the horizon. So any x equals is a vertical line. I'm going to call that Mr. X or dad, and then mom is going to lie down here. And we're not going to cross mom or dad unless we have to, and I'll talk about that today. Mom's full of love, mercy, tender, and grace, so we can cross the horizontal asymptote if we have a good reason to, or if we have a point to get to, but I would never cross dad. So I'm just going to get close to dad on this side, and then instead of crossing over left to right, it'll pick up it'll switch from positive infinity to negative infinity. And again, no reason to cross mom here, the horizontal asymptote. So there's your first look. We're also going to be talking about the domain. The domain is going to be all reals except you can't let x be where the vertical asymptote's at. You can't cross dad. So the domain is going to be everything from left to right except for where dad's at. And dad's at x equals negative 5 here. If you were to factor this, this would be x plus 2 and x minus 2. So there's 2 dads in the house. And so I would say, it's all reals except the 2 dads, positive 2 and negative 2. Here, when you set x squared plus 1 equal to 0, you actually get an imaginary. So there's nothing that would cause havoc in the denominator here, so it's all reals. Again, nothing's going to cause havoc here, so I would say the domain is all reals once again. Here, we don't want to let x be 1, so I would say all reals except x can't be at 1. So we've got a vertical asymptote at 1. However, this is a trick problem because if you were to factor the numerator to x plus 1 and x minus 1, notice that this is actually not even a vertical asymptote because these x minus 1s cancel. This is called a removable for the function, and that creates a hole in the function instead of an asymptote. So instead of a vertical asymptote, you actually have a hole at x equals 1, and I'll talk more about that later. But nonetheless, we still can't let x be 1 in the original function, even though that cancels. I would still say the domain is all reals except x can't be 1. So I hope that helps about domain. So every time you run across graphing something, I would try to explore 4 things. The vertical asymptote, the horizontal asymptote, which I'll talk more about. There's 3 scenarios for that. The x-intercept and the y-intercept. Those are 4 good things to look for when you're graphing. So to find a vertical asymptote, I'll give you some notes on this. We set the denominator equal to 0. So whenever x squared equals 0, that's when x equals 0. And this is the first time that you've actually seen a double asymptote. So this is actually x minus 0 and x minus 0. If I write it like this, you can actually see I've got a double asymptote. Now, in section 5.1, we talked about a double root bouncing. Well, a double asymptote is not going to alternate from positive to negative. It actually looks like a volcano. It's going to head in the both direction, either both positive direction or both negative direction, and I'll show you that in a moment. Since the degree of the numerator is less than the degree of the denominator, then I know my horizontal asymptote is going to be y equals 0, and I'll give you notes for that in just a moment. The key for this is this double vertical asymptote. How does that cause the function to behave? So to find an x-intercept, I try to set the numerator equal to 0. Well, 1 never equals 0, so there's no x-intercept. And then the y-intercept, again, I can't divide by 0. So again, there's no x-intercept, no y-intercept, which means I need to do my let statement. So if you let x equal 1 again, then my y will turn out to be, 1, 1 again. So, but this is interesting, because if you let x be negative 1, well, I shouldn't have to. If this goes to positive infinity on this side, since it's a double asymptote here, it's going to go to positive. So instead of alternating, they go the same direction. If you want to check that out, all you have to do is let x be negative 1, and then check 1 over negative 1 squared is also a positive 1, and that picks up this point. So you can see I kind of missed a little bit. That's not really the point. The point is they head in the same direction for double asymptotes. So whenever you have a double asymptote, it's going to cause this, I'm going to call it a volcano effect. So there's a little bit better picture of what this graph looks like. So this is going to be a volcano effect at 2. The graph is going to either swoop positively towards 2 or negatively towards 2, depending on the value of a. And it's going to be shoved up 1 unit. So this actually is the first one that you're going to see it has a D shift. So my center is going to be here. So in other words, the asymptote is here, and the asymptote is not going to be at y equals 0, since the numerator is less than the denominator, degree of the numerator, but it gets shoved up 1. So now my asymptote's at y equals 1, and another vertical asymptote's at x equals 2. Again, you can plug in some values here. Like if you could plug in a 3, I think it's going to be at 3 too. So if you let x be 3, you could just do a quick tester point. Actually, I don't have to do a tester point. I could find y-intercept, x-intercepts. But if we continue with this, 3 minus 2 is 1, 1 squared. So 1 plus 1 is, there it is, 3, 2. I've got my nice point right here. And I know I have symmetry, and it's heading in the same direction, so another volcano effect. So again, this is called the horizontal shift. It went to the right 2. And this is called the vertical shift. It went up 1. So all the asymptotes and the function get shoved to the right and up. So boom, there's that point, 3, 2 that we discovered. If you want to plug in some more points, you can. This is called your horizontal asymptote. Again, I'm going to talk about the degree of the numerator and the degree of the denominator to try to help. This is the book's version of what's happening at horizontal asymptotes. This is your double asymptote that's forming the volcano effect, heading in the same direction. If it's just x, if it's just a single root like x minus 5, then this would be x equals 5, and notice that it's alternating. It's going to positive infinity on the right, negative infinity on the left, and it might be the opposite direction, depending on if it's positive or negative. Oblique means if the numerator is greater than the denominator, then we end up with this slanted asymptote, and we're going to find the equation of that by dividing. I'll show you an example of that too. Oblique just simply means slanted. I'll show you how to find the equation of that slanted in just a moment. So vertical asymptotes, remember, we're going to set the denominator equal to 0. So looking at finding some vertical, this one, if we set the denominator equal to 0, we'd get x equals negative 3. This one, I've got 2 dads in the house, 2 vertical asymptotes. One's at 2, one's at negative 2. This one I would actually have to factor. Factors of 4 that add up to 5. So x plus 1. And I would say what? X equals negative 4 and x equals negative 4 and x equals negative 1. And this one I would factor this one as well. X plus 2, x minus 2. So 2 dads in the house again. But they tricked you. Thank you. If you were to factor this, one of these is removable. So this x plus 2 and this x plus 2 actually gets removed. So you actually have a whole at negative 2 comma something. And to find out where that hole is, I take that -2 and plug it into the remaining function. I'll show you an example then as well. So remember, it's not a vertical asymptote if it's a removable. So this is talking about, again, single roots. We're going to alternate from positive infinity to negative infinity. If it's a double root, we've got this volcano effect. If it's a triple root, again, it's going to alternate from positive. So if it's odd, it's going to alternate. If it's even, it's going to end up with this volcano effect. You can explore this on your graphing calculators, although I would be trying these without a graphing calculator because on your test, there will be no calculators allowed. Oblique simply means slanted, and that means that the numerator is going to be greater than the denominator. And to find the equation of the oblique asymptote, again, we're going to divide. I'm going to give you notes here in just a second. Here's how to find those horizontal asymptote. Here it is. If the numerator is less than the denominator, then this is y is at 0. So here it is. Here's the degree of the numerator is a 1. The degree of the denominator is a 2. So if the numerator is less than the denominator, the horizontal asymptote is at y equals 0. This one says if the numerator degree is equal to the degree of the denominator, then y equals a over b. Some teachers teach it a over c. So if I have 3x squared plus 5 over 7x squared minus 9, then notice that the degree of the numerator is equal to the degree of the denominator. The degree of the numerator is a 2. The degree of the denominator is also a 2. Even if I were to change this to 9x, that's not going to change the degree. The degree of the numerator is the same in the numerator as it is in the denominator. Then you check out the a over b, or the coefficients out front. In this case, the horizontal asymptote would be at 3/7. And then this last scenario, you would divide, and I'm going to show you that example of that in just a moment. Actually, here it is. The degree of the numerator is greater than the degree of the denominator, so I'm going to synthetically divide. Weesh, this will not be fun. I can't synthetically divide because the root sucks, so I'm going to do long division. Plus 0x plus 1 into 3x to the 4th. I'm going to add some zeros here since x cubed, 0x cubed, minus, let's do this again, 0x cubed minus x squared plus 0x plus 0. So here we go. I'm going to synthetically divide. How many times does x cubed go into 3x to the 4th? Probably 3x times. So I'm going to throw a 3x on top of my other 3x, lining up like terms. And then I'm going to multiply, stack, and add. So 3x times, didn't quite get far enough, 3x times x cubed is 3x to the 4th, which I wanted to line up like terms for. 3x times negative x squared is negative 3x cubed. That's interesting. Keep going. So this is a 0x squared plus 3x. So I'm going to subtract and get a positive, because I'm going to subtract off a negative, and that'll change that to positive. And repeat this process. How many times is x cubed going to 3x cubed? Well, that would be 3 times. And I can stop. I know I've got the remainder here, but the equation of the oblique asymptote, the first number is your slope. So here's your slope, the 3, and the y-intercept is also a 3. So this isn't very interesting, but 3x plus 3 is the equation of the oblique asymptote. Hey, if the degree of the numerator is equal to the degree of the denominator, all we have to do is look at the coefficients out front. So in this case, the horizontal, it's not oblique, it's horizontal because the numerators are equal to each other. It would be 8/4, which is y equals 2. Again, the degree of the numerator is greater than the degree of the denominator, so I would do either synthetic division or long division here. I'm going to skip this example, but I would probably do long division to find the equation. So again, this is talking about the book's rules. You can read through those if you want. And here are some multiple choice. So I'm going to attach on Blackboard a worksheet that I'd like for you to follow along with. Maybe you could try to work them out before. But here are the rules that I use to find. I would always find the vertical asymptote first. I need to redo this worksheet. So find the VA first. I'll try to stay consistent. Find the vertical asymptote first, then find the horizontal or the oblique asymptote second. Find the x-intercept third, so VA, HA, x-intercept, and y-intercept. And I think my math lab will ask for the domain, but remember, the domain is just always all reals except for where the vertical asymptote's at. So let's start with the vertical asymptote on this. Again, I'll attach a PDF file to Blackboard that'll have this worksheet. So if you want to print that off and follow along on this video, you can. and remember, it's very easy to watch me work these problems, but if you try them for yourself, it's not so easy. So I would recommend you to try to graph some of these before I do. So looking at setting the denominator equal to 0, we get x equals plus or minus 1. I can't factor the numerator, so just leave that. So nothing's going to cancel. There's no holes. To find the horizontal asymptote, I look at the degrees of the numerator and the degree of the denominator. Since the degree of the numerator is 2, the degree of the denominator is 2, they're the same. Then I'll do that a over b in case 1 over 1. And I'll graph y equals 1. To find an x-intercept, I set the numerator equal to 0. Well, x squared plus 1 never equals 0. Again, imaginary. So there's no x-intercepts. And the y-intercept, hopefully easy. You just let every x be 0. So I'm going to look here in blue. 1 divided by negative 1 is negative 1. And at least I found a point. Well, I think I have enough information to graph this. I'm going to start at the point, the only point that I have, swoop toward the asymptotes. If these goes to negative infinity, they're going to pick up in positive infinity. If this side goes to negative infinity, it'll pick up in positive infinity. And I'll just keep swooping. If you don't like that and you want to find specific points, you can plug in for x and y, but I don't care for you to do that. I'm just looking for generalities. I want to see, I'll give you 1 point on your test for the vertical asymptote, a point for the horizontal, a point for the x-intercept, a point for the y-intercept, and then 1 point for the graph. And I don't really care if the graph comes down here or not, so I wouldn't spend time plugging in for x and solving for y. Here are the correct solutions to that graph, and hopefully we got everything correct. Let's try the next problem. It says, let's find the VA first by setting the denominator equal to 0. Well, x equals 0 when x equals 0. That means we got a vertical asymptote as like x equals 0. Horizontal asymptote, aha! The degree of the numerator is greater than the degree of the denominator, so I'm going to do either synthetic division or long division. I'll try long division 1 or 2 more times, and then I'll switch over to synthetic division to show you that both of them will work. X goes into x squared x times x is x squared plus 0x. And oh boy, x doesn't go into 0x at all, so it's just y equals x is the equation for my horizontal asymptote. And y equals x really means start at 0 and do rise 1 over 1. So it's a 45-degree angle. Y equals x. Let's go for x-intercepts by setting the numerator equal to 0. So when does x squared plus 1 equal 0? That'd be never. So there's no x-intercepts, never cross the x-axis. And the y-intercept is letting every x be 0, but you can't divide by 0, so I would say none there as well. Darn, I don't have any x-intercepts or y-intercepts. This is where I would do my let's scenario. Let's let x equal, let's go 1. So if you let x be 1, then y will equal 1 squared plus 1 over 1. How about 2? So I'm going to go over 1 up 2. So I know I've got a point inside here. And then I'm going to swoop toward the asymptotes. So this is your oblique asymptote. And if this goes to positive infinity, it's going to pick up at negative infinity down here and continue swooping. Remember, when all is said and done, these need to be functions, which means they need to pass the vertical line test. So sometimes I have students creating x-intercepts. Well, I can't graph this black line because that would create an x-intercept, and you told me that there was none. But also, it doesn't pass the vertical line test. So make sure that when you do your tests or you're working these out, they actually pass the vertical line test. So there are solutions to number 2. Number 3, to find the VA, I would set the denominator equal to 0. And to do that, I would factor. So 2x and x are the only factors of 2 that I know. It's either 1 and 3 or 3 and 1, but I know that I need to find factors that differ by 1. So I'm going to stick the 3 here and the 1 here. So my outer terms are 2x and my inner terms are 3x. And I want the larger term to be negative. So I'm going to make my 3x positive, forcing this to be negative. And now you can see I've got x equals negative 3/2 and also x equals 1. So there's my x equals 1, and negative 3/2 is around 1.5. And if you label it, it'll be true. The y-intercept, the horizontal asymptote, since the degree of the numerator is a 0, the degree of the denominator is a 2. I know the numerator is less than the denominator, then y equals 0. The x-intercept is found by setting the numerator equal to 0, and that's going to be a big none, because 2 never equals 0. To find the y-intercept, we let every x be 0, and to do that, I think I'm going to get this 2 over -3, because everything else will be zeroed out. So how about 0, how about 0 comma negative 2/3? So at least I have a point. 0, negative 2/3 is somewhere down here. So I think I'm going to swoop toward my asymptote again. So starting here, no reason to cross because I don't have any x-intercepts, so I know I can't go up. And I can't go left because that's crossing that. I can't go right, that's crossing that. So the only place I can go is down. Again, I'll show you some examples of why we want to cross the horizontal if you have a point. But there's no point to cross the horizontal here. In fact, we can't because that would create x-intercepts. If this goes to negative infinity, it's going to pick up in positive infinity. Swoop, swoop. If this goes to negative infinity on this side, it'll pick up in positive infinity. So I'm going to swoop down again. And that's example number 3. And it looks like we have the same answer here. So example number 4. Again, these are my rules if you haven't got them down yet. To find a vertical asymptote, you set the denominator equal to 0. To find the horizontal asymptote, it's 3-pronged. If the numerator is less than the denominator, then we got y equals 0. If the numerator is equal to the denominator, then we choose the coefficients out front, a over b. And if the numerator is greater than the denominator, it's oblique, and that's when we're going to divide. To find the x-intercept, write these notes down. To find an x-intercept, we set the numerator equal to 0. That's only true if there's no d shift. If there's a d shift, we actually have to let y be 0, but most of the functions don't deal with d shifts. So this will be a good rule. Instead of letting y be 0, you can just set the numerator equal to 0 a little bit faster. To find the y-intercept, we let every x be 0. So those are the rules that we're using for each problem. This one's kind of interesting because if I set the denominator equal to 0, then there's none. So there's no vertical asymptote, no dads in the house. To find a, that's VA. To find the HA, it's the horizontal. It looks like it's, wow, interesting. The numerator is greater than the denominator, so it's oblique. So I'm going to have to divide x squared plus 0x plus 4 going into x cubed plus 0x squared plus 0x minus 1. So in this case, x squared goes into x cubed x times. Ooh, didn't quite work out like I thought. All right, there it is, x times, getting close to the top here. So this is x cubed plus 0x squared plus 4x, and I got a 0x squared, and x squared goes into 0x squared 0 times. So again, it's y equals x, 45-degree angle. To find a x-intercept, you set the numerator equal to 0. When does x cubed minus 1 equal 0? Well, that's when x equals 1. So I actually have an x-intercept here. And the y-intercept is letting every x be 0. It looks like it'd be, in this case, highlighting this negative 1/4. So 0, negative 1/4. So this is kind of interesting. I've got 2 points. I can connect those 2 points. Kind of forms a little bump, but I want to get close to the asymptote here and close to the asymptote here. If you were to graph this on your calculator, you'll actually see this graph actually crosses the oblique asymptote and then comes back, but you don't know that. So without a calculator, I'll know that you're cheating if you're using your calculator and you actually graph the correct function, which I don't want. So please don't use your calculator. There's nothing that we have that would indicate that this does cross, unless you actually did a quick t-chart. So if you do this, then show me that you're actually plugging in a 5 and actually realizing that this number is greater than, it's I don't know, 5.5 or something. Because 5 is where the 45-degree oblique asymptote's at. So if this turns out to be 5.5, then you know that this crosses. But we don't have any indication that this does cross. So, and I would not plug in for x and solve for y. So my final graph would just look like it would stay close. It would be a little bump right here, down in here. And I would just stay below that asymptote. But in all reality, if you were to check this, this actually does cross. And you don't know why yet, and I am not explaining why, but this would be my final graph. For this one, to find the vertical asymptote, we set the denominator equal to 0, and you get plus or minus 3. To find the horizontal asymptote, since the degree of the numerator is less than the degree of the denominator, we're going to choose y equals 0. To find the x-intercepts, set the numerator equal to 0, so that's going to be a 4. This is kind of interesting because this is your first one where you've actually got a reason to cross mom. We have a point on mom, and we're going to cross her because, well, it's a single root. We have to pass. If it was a double root, we'd bounce right there. A triple root, we'd twist and shout. So the y-intercept, letting every x be 0, looks like in this case it's going to be 4/9. So notice that I'm being very careful. There's not just numbers over here. For the vertical asymptote, it's an equation. X equals the horizontal is an equation. It's not just a number. Y equals. X-intercepts are ordered pairs and y-intercepts are ordered pairs. So please give me more than just numbers over here. So 4/9 is a positive value. So this is kind of interesting because some students will try to connect this. But remember, we can't cross dad. Mom's full of love, mercy, tender grace. But dad, I'm so sorry. Actually, dad was the pushover in my family and mom was actually the very strict one. But for this scenario, I'm going to say dad is very strict. Don't cross dad. It works better for my analogy. So if you can't cross dad, I'm going to stay away from this because I don't really know if this looks like purple or if this comes down and looks like red. So I'm going to avoid because I don't know if it's purple or red. So I'm going to start actually in between the two dads, and there's no reason to cross. In fact, I can't go down because that would create x-intercepts, which I do not have. I can't go left, crossing dad. I can't go right, crossing dad. The only way I can go here is swooping up and swooping towards dad. If this goes to positive infinity, I know it's going to start in negative infinity, and now I'm convinced it's the purple and not the red. Because, oh, and by the way, don't go off into la la land. When you cross mom, she's full of love, mercy, tender grace. Come back to her. Mom loves you. Come back to her. So I'll erase this red because now we know that that's wrong. And then continuing graphing, if this goes to positive infinity on the left, it's going to pick up from negative infinity and no reason to cross. I don't have a point to get to. So this is kind of interesting. It does cross on this side. It forms a little bump. Don't just go right along, and because then I think it's kind of, I don't know what's happening there. If it's bouncing off, you don't want to bounce because that's not coming close to mom. So actually pass through this point, which causes a little bump here, so it's not symmetrical. They don't have to be. And there's the final solution here. This one, let's keep going. Vertical asymptote. It doesn't look like there's any because when you set that equal to 0, you get an imaginary number, so no dad in the house. The horizontal asymptote, since the degree of the numerator is less than the degree of the denominator, Mrs. Y is at 0. We're going to horizontal asymptote at y equals 0. The x-intercept is going to be 1, setting the numerator equal to 0. And setting the denominator, letting every x be 0, I'm going to get this negative 1/3 value. 0, negative 1/3, which creates a point here, 1, 0, x-intercept, and negative 1. So again, that's kind of interesting. A good reason to cross mom. It's a single root, x minus 1 to the first. So it's a single root at x equals 1, which means I'm going to pass through and then come back to her. And no reason to cross mom on this side. So again, you can pick up your calculators and check these, but the goal is to be able to do this without a graphing calculator. There's the final solution for number 5. Number 6, again, continuing on. The vertical asymptote is going to be x equals plus or minus 1. So 2 dads. Each problem is just a little bit different. So I'm so sorry. You might think that you understand, but the hard part is trying to graph these things after you have all this information over here. Horizontal asymptote is y equals 0 because the degree of the numerator is a 1. The degree of the denominator is a 2, so Mrs. Y is at 0. The x-intercept is found by setting the numerator equal to 0, so it's x equals negative 1. And the y-intercept is also negative 1. Oops. These should be points. So this one should have been a point. Let's actually make it. The x-intercept is negative 1, 0. So there. Oh, no, it's not. Because you can't cross dad. I forgot. This is, so I knew something was wrong because you have a point on dad, which is impossible because we can't cross dad. So I'm going to erase that whole asymptote. In fact, I'm going to erase the vertical asymptote. How come? Because I'm going to remove this factor, and I am left with just x minus 1. So what happens at a removable? This causes a hole, and the hole is going to be at x equals negative 1 because that's what I get when I set that factor equal to 0. So the only vertical asymptote is x equals 1. A horizontal asymptote stays the same at y equals 0. So I'm really looking at this function now. The degree of the numerator is less than the degree of the denominator. My x-intercept, this time my x-intercept is a big none. Because how come? 1 never equals 0. So I would say none. There's no x-intercept. And the y-intercept is still at -1. Because now I'm looking at letting every x be 0. So I've got a point here. So now I'm swooping here, swooping here. If this goes to -infinity, I pick up in positive infinity. But I need to go back and put a hole at x equals -1. And if you want to find out where the hole is, which I would like for you on your test to identify the hole, just plug in a -1 here. So 1 over -1 minus 1 is 1 over -2, or -1/2. So we should have a hole at -1, right there. So just take your eraser on the day of the test, erase this little spot, put a hole here, so I can clearly see. That's not going to show up if you graph. It'll just look like a normal hyperbola with no holes. But if you hit trace -1, enter, you'll get no y values. It's an empty set. This hole is not defined. So be creative when you write your holes. Exaggerate this for you. So again, if we learned anything, we want to check for removables. So we should factor this thing first. So factors of 3 that add up to 2 are 3 and 1. Signs are going to be alike. They're both negatives. And there's no removable but 2 vertical asymptotes. So x equals 3 and x equals 1 for my vertical asymptotes. My horizontal asymptotes, since the degree of the numerator, is greater than the degree of the denominator, I'm going to do division. This time I'm going to do synthetic division because the root is really nice, -2. So for those people that have never done synthetic division, 1, -2, 3, bring down the first term, multiply, -2 times 1 is -2, and add -4. So this is the first time that you're seeing the oblique asymptote other than y equals x. This time this is your slope, so it's 1x, and there's your y-intercept -4, which means start at -4, rise 1, run 1. So there's my oblique asymptote. I'm going to go back and graph in my x equals 3 and x equals 1, my vertical asymptote. Let's go see if we can find some x-intercepts. By setting the numerator equal to 0, it looks like a 3, 0 and a 1, 0. Holy cow. I don't have x equals... No. Oh my gosh. I knew something was wrong because I have a point on the asymptote. My vertical asymptotes were wrong. Vertical asymptotes should have come from the denominator. Sorry about that. This should have been x equals who? -2. Oh my gosh, what was I doing? I need to take a break. So I'm getting rid of these vertical asymptotes and trying to put in the correct vertical asymptote at x equals -2. Is that better? So now I've got x-intercepts at 3 and 1. Could be a little bit better. The y-intercept is worth 1 point on your test. All we have to do is let x be 0 and look right here. That would be 3/2. Label it, get close to it. That's around 1.5. So it looks like I've got a couple points that I can connect because I'm not crossing dads. So I'm going to pass through here. It's going to go below, get close. If this goes to positive infinity, it's going to pick up in negative infinity and get real close to the oblique asymptote. So it looks like there's some symmetry here. This probably doesn't look as funny as I actually drew it. Probably a nice smooth curve. So there's a... How come I have x-intercepts of none? Factors of... Oh my gosh, I need to quit. This is... Factors of 3 that add up to 2 are not 3 and 1. 3 and 1 adds up to 4. What was I doing? I gotta quit. So my x-intercepts should have been none. Holy buckets. I can't factor this. So I really should check. Just because it's not factorable, I can't really say none. I really should check the quadratic formula. -b plus or minus the square root of b squared minus 4 times a times c. And now I can see that all of this is a negative number, 4 minus 12. So I'm taking the square root of a negative, and that's what causes it to be none. So this graph is actually incorrect. There should be no x-intercepts, and I only have a y-intercept. Oh, I totally botched this. So the graph looks more like this. Oh, well, I made some mistakes. Hopefully you won't make the same mistakes on your test. So I'll go a little bit slower this time. If there's anything I've learned is I want to look for a removable by factoring first. This is x squared minus 4. This is my favorite topic. Factor some more. Replace the graham crackers. Replace the graham crackers. Replace the Hershey's with this Reese's peanut butter cup. We've got great s'mores. So keep factoring some more. Factors of 2 and 9 that differ by 1. Maybe it's not even possible. So let's see, 3 and 3, 6 and 3, not good. 9, not possible. Again, let's use the quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c. Holy buckets. All over 2 times a. It looks like it exists this time. If I multiply all of this pink together, I get something close to the square root of 72. Oh, without a calculator, this can get a little bit miserable. The square root of 72 is close to the square root of 64, which is 8, and the square root of 81, which is 9. So somewhere around 8.5. I think I've got x-intercepts, but they are not nice x-intercepts. And I'll show you how to guess what it is. I'm going to guess like 8.5. So it's negative 1 plus 8.5 divided by 4, and negative 1 minus 8.5 divided by 4. So this is just a horrible problem. But the vertical asymptotes are easy. Positive 2 and negative 2. X equals plus or minus 2. The horizontal asymptote's not bad, since the degree of the numerator is a 2. The degree of the denominator is a 2. Then we're going to do y equals 2/3. That's somewhere in between 0 and 1. Just label it will be true. The x-intercepts, I just found them. Oh my gosh. They're somewhere around, let's do this, positive 7.5 divided by 4 is somewhere around a little bit less than 2. Doesn't even matter. Somewhere less than 2 is an x-intercept, so it's on the left of this vertical asymptote. And then negative 1 minus 8.5 divided by 4 is around negative 2 point something, a little bit more than negative 2. So again, I don't even really care. I just needed to figure out if it was to the left or to the right of these vertical asymptotes. What would I write for the answer? Probably the exact answer. The x-intercept, letting y be 0. So there's the exact answer. But I needed to find these red and purple points to locate how to plot the function. The y-intercept, again, is letting every x be 0. So how about 9/12? And 9/12 reduces to 3/4. And it's positive. So we'll go to, let's see, this was, where was this at? This line was y equals 2/3, which is 0.666. 3/4 is a little bit above that. Holy cow. This is tricky. So I've got a y-intercept above. Oh my gosh, this is a great problem though. So let's see. I cannot, well, I can cross mom, but I don't want to if I don't have to. So let's see, I can't go right because then I'd miss that point. If I go up and then kind of grab, and it doesn't pass the vertical line, I think I'm going to have to cross mom here because I'm just checking. I can't go left, I can't go right, and I really can't go up because it doesn't pass the vertical line test. So mom's going to have to forgive me. Looks like I got a good reason to cross her here. Maybe I shouldn't even start it on the side. Maybe I should have started with this point because the only thing you can do here is pass because that's a single root. If this goes to negative infinity, I know this starts up in positive infinity, and this comes down, passes through this point. It's the y-intercept, passes through this. It's a single root, so just keep passing. So that kind of verifies it. I have to cross mom. If this goes to negative infinity, I pick it up in positive infinity and swoop again. So this was a great example of using the quadratic formula to find the x-intercepts, and also a good example of where you might want to have to cross mom. There's another solution. It looks like I used a calculator, but hopefully you won't have to do that. All right, so finding the VA again, setting the denominator equal to 0, I would say none, because you can't take the square root of a negative. The degree of the numerator is less than the degree of the denominator, so I'd say y equals 0. The x-intercept, setting the numerator equal to 0, that's never, so there's no x-intercept. And the y-intercept is letting x equal 4. 0, 4. So I'm going to say there's no vertical asymptote. I got a horizontal asymptote. All I have is a point at 4 and no x-intercept, so I start here. Sometimes some students are going to try to graph this really boxy. But remember, these are nice, smooth, continuous functions. So you don't want to swoop this way, because that'll form a sharp edge. So I would swoop this direction, making a nice hump or a nice mound here and heel. Right? That was kind of an interesting function. So again, I'm going to give you a worksheet, and I want you to try to work through these problems before I try to work through them. So go to Blackboard, print this off, and say, oh, we should do this one. Vertical asymptote, it's a double vertical asymptote. Remember, we're not going to go opposite direction. We go the same direction. This is a volcano. So we got x equals -2, and sometimes I write it twice to try to remind myself that this is going to be a volcano effect. Either it's going to swoop up to both sides or it's going to swoop down. I don't have enough information yet to find out what it is. Let's keep finding some more information. The horizontal asymptote is going to be, since the degree of the numerator is a 1 and the degree of the denominator is a 2, if I multiply that out, y equals 0, because if the numerator is less than the denominator, then y should equal 0. X-intercepts found by setting the numerator equal to 0, so we'd say -8, 0. So the x-intercepts, that's what, oh, this is cool. It's going to cross mom, because I have a point on mom. And that's x-intercepts. And then the y-intercept, oh, be careful, letting every x be 0. So 8 over 4, because 2 squared is 4, is a 2. So 0, 2. So I'm going to start at that 0, 2 and swoop toward the asymptote. And you know, you might think that you're down here crossing, but you're actually not. Remember, this is a volcano. So I'm going to stay up here, cross through mom, and then don't go into La La Land. Come back to mom. So after you cross mom, don't swirl around and do crazy stuff here. Don't bounce through mom, because it's not a double root. I just have a single root. It's x plus 8. If this was squared, then I would bounce through that thing. But since this is to the first power, I'm just going to pass through mom, or pass through the x-intercept and come back to mom. She's full of inversion tender. So again, there's not symmetry and not bugs, students, but we'll live with that. So there's a little bump down in here. You can verify this in your calculator, but I'd like for you not to use your calculator at all. We'll keep going here. Number 12, I've got VA, setting the denominator equal to 0, x equals -1. The HA is, well, since the degree of the numerator is an x squared, it's a negative x squared, and the degree of the denominator is also an x squared. I'm going to do that a over b, which is -1. That's interesting. So I'm doing that coefficients out front, and that's -1 divided by 1. So I have a -1 up here, and I have a +1 down here. So I got a vertical asymptote, horizontal asymptote. Next thing I'm going to look for is x-intercepts. By setting the numerator equal to 0, that'd be 4 and 6. I'm going to write those as ordered pairs. I'm going to plot 4 and 6. And then the y-intercept, by letting every x be 0. So it's -4 times -6 all over a 1. What is that? -24? Eesh, that's way off my graph. But I'll plot it way down here, and then I'll just, well, it's off my graph, but I'll just label it and it will be true. So again, most students can get to this part, but then they kind of falter on how to graph these things without a calculator looking at it. Sometimes it's difficult because we don't know if it swoops underhand like this or if it swoops overhand. I know that it does not just go flat. That's a constant function, so it's either swooping over or under. Since I have to get to this y-intercept, I'm presuming it's swooping over, because, and I have to cross mom because that's the only way to connect that dot to this dot, which I can because there's no vertical asymptote. Don't cross mom again though. Just get close to her. No reason to cross. If this goes to -infinity, it should alternate unless it's a double root. So looking back, oh my gosh, really change my viewing. Sorry about that. Oh my gosh. So looking at the original function again, looks like I had a double asymptote. So I probably should have written this twice to kind of try to remind myself that this is going to be a volcano. I'm not going to alternate. So if this is going to negative infinity, I cannot start in positive infinity. I need to actually start in negative infinity down here. And this is going to swoop. In fact, if I would have tried to have drawn this up here, I would have run into some problems because in order to get close to mom, I would have had to create another x-intercept, which does not exist. So I know I can't swoop up here. So there's a couple telling signs that it's a double asymptote. So this asymptote continues going down here, the function continues going down, and it swoops over here. Again, no symmetry, but that shouldn't bother you at this time. I've shown you enough examples where that shouldn't be a problem. You should try some. There's number 13. There's the answer for it. Try it, and I'll end this session here because I've gone 45 minutes. Good luck.